Can keep that on hold for now. Am I?
Yes. Yes.
Hello.
Hi, Prof.
Yeah, you can hear me
Yes.
and you can see the screen also.
Yes.
Yeah. So shall we start for today?
Oh,
Hello.
yes. Yes, Prof.
Yeah.
We've been waiting for you. You can proceed.
Okay. So hello everyone. Today we have a session on uh, deep learning. So we run through this PowerPoint, which basically tells us what do we mean by deep learning, and we try to understand what's the difference between machine learning and deep learning. Okay, so uh, the deep learning is a special type of machine learning. All deep learning is machine learning, but not all machine learning is deep learning. Okay, so what's the difference? In machine learning, the machines learn patterns from examples using selected features or measurements. And in deep learning, the machines learn patterns using neural networks with many layers, often directly from the raw data. See, for example, if you have, say, fruits, we have an orange, an apple, uh, and a tomato, and so on. In machine learning, we tell the features to the machine. We train machines on the basis of features. We say if it is round, and if the skin is rough and the color is orange, then it is an orange. But if it is round and it is red, then it could be a tomato or a apple. And then you specify further what are the features which distinguishes between an apple and a tomato. Right? Similarly, attributing the same thing to an astronomical example, if you have images of galaxies, we say that if the shape of the galaxy looks like an ellipse, if it's minor axis and major axis of this type, it's called E0, E1, or E7 galaxy. In spiral galaxies, you have spiral arms and it has a disk, a bulge, and a halo. So you specify the features. So in machine learning, the data is structured and often it is tabular, like it shows in this slide. So, for example, you have the ID of the objects, you have magnitudes, you have the color, you have the redshifts, and so on, right? So the features which you say are what is the magnitude, what should be the color, what is the redshift, so on, and then you train it on the basis of features. And then the machine learning models, they train on the basis of these features, which it makes these decision trees and uses some algorithm like the random forest or SVM. And then it starts classifying or identifying objects. While in deep learning, we don't have these features. There's no manual feature engineering. See, for example, we give oranges and apples and tomatoes, and the machine itself learns to differentiate between the two. We don't specify what are the features the machine should look into it. It itself tries to, from the raw input, for example, in case of astronomy, you feed various images of galaxies, and it looks through the galaxies, and by itself, it tries to find out the features. We don't specify what are the features, what are spiral arms, and what kind of a spectra you require to classify in O, B, or A class. While the machine itself learns to find these features and does it. So that's the basic difference between machine learning and deep learning. So deep learning learns representation from raw data, right? And it goes through various the filters and picks out the features on its own and then starts classifying that. So they can embed in hidden layers. And we will do some examples for identifying, say, uh, uh, s- galaxies, spiral lenticulars or elliptical galaxies from the list, how CNN does it, and or how it looks into the and finds out whether it's a gravitational lens or a supernova or so on. So machine learning, deep learning learns from raw data. It automatically discovers useful features and representations and uses deep neural networks. It has multiple layers, complex models and nonlinear relationships, and um, it excels with large, right? So deep learning is very good when we are dealing with very large complex data sets. And it's okay. So both approaches are complementary, and the best choice depends on the data, the kind of problem we are using, and the amount of available data we have. So to reiterate the basic difference, in machine learning, we use the technique of teaching a computer to learn patterns from data without explicitly programming every rule, right? This is what we saw in our previous class where we studied machine learning techniques and so on. So example, the rule we avoid hard coding. If a star is red and faint, classify it as M-type star, right? This was the traditional methods. But in machine learning, we don't specify that. Instead of writing every rule manually, we provide examples of stars with known classes and let the model learn the patterns. In deep learning, a neural network-based form of machine learning with many layers, it learns complex patterns from raw data. It's useful for images, for spectra, for light curves, and for simulations, and often reduces the need for manual feature design. We don't specify what are the features which you should look for, like we have to do it for the machine learning. And it is used to when you are dealing with images, for example, through galaxy surveys, we have many billions of galaxy images, and it looks at these images and starts classifying, identifies features on its own and classifies them. Or if you have spectra of a large amount of various stars, it looks at the spectra and tries to identify features and bins them into different categories and so on. We don't have to specify that if the color B minus V is this, then it is O star. If it is this, it is B star, like we would do it in machine learning. And then we feed a lot of light curves, and by itself, it starts analyzing that certain light curves look similar and others look different and starts classifying them, right? And even with simulation data, it is very useful. So deep learning, it is used when you have tremendous amounts of data and the patterns are very complex. And it often reduces the need of manual feature design. Yeah, so like I had specified, in machine learning, we specify color if it's red, orange, or green. We specify the sizes, if it is small, medium, or large, or whether the shape is round or oval, or the texture is smooth and rough. So you specify features in that, and then we train models such as a decision tree, random forest, or this support vector machines, or logical regressions uh, to then these trained sets uh, can be run on the remaining data, and it starts classifying or identifying objects. While in deep learning, it gives the model the raw image itself, and the early layers learn its edges, right? So first it finds out how many edges are there, whether they are 4 to make it a quadrilateral, and then it starts looking at the sizes and says it's a square or a rectangle and so on, or whether The middle layer learns the curves and textures, and the later layers learns the whole shape, right? For example, if you have these fruits, it first identifies whether it has edges or not, whether it's a smooth one, whether it's circular. Then the middle layer looks at the curves and the texture of it, and then right identifies what it is. So the key difference, like I said, is machine learning often depends on human design features, while deep learning features automatically from the raw data. So, and for an example, if you have say star 1 and 2, and its G magnitude is 14.2 or 10.8, and the color in the B and the RP colors is 1.5, 0.2. The parallaxes are given to be 2.1, 0.7, and the proper motion is 5.3. And this we are specifying all the features, then you classify them as a main sequence star or a giant star, right? So this is what it does. So machine learning will specify these features and you train it on that. So model learns from numerical columns such as these magnitudes, colors, parallax, and proper motion, and a structured table of measures of astrophysical quantities are given and we train it. So machine learning methods in astronomy, as we had seen, we have these random forests, we have support vector machines, we have k-means clustering, dbScan, HDBScan, Gaussian mixing models, which we had seen in previous ones. And this random forests, as we had seen, it's usually used in classification of stars, galaxies, or quasars. You know, you have it finds out whether it's an object is a star or a galaxy or a quasar from the features which we provide. And SVMs are used in separating stellar populations into different groups. It's used in classifications. It can also be adapted for regression. And in SVMs, the primary task of an SVM is to find the optimal decision boundary or the hyperspace that separates different classes of data while maximizing the margin between them. Right? And it is HDBScan, DBScans are finding members in open clusters, whether identifying it's an open cluster or a moving group, let's say association, or it can be used to identify member stars from the field stars and so on. Again, Gaussian mixer models are used for modeling stellar populations and used for membership dissemination and various things, which even Priyana had shown in the last session. So the important point is the traditional machine learning can be very powerful when the input features are informative, clean, and physically meaningful. Okay, so when we are looking at morphology of galaxies, by looking at the morphology, we classify them as spirals. Like we all know that galaxies come in many shapes, sizes, and colors, reflecting their various formation histories in the physical processes which shape them. So spiral galaxy mostly has a disc-like structure. Then it has a halo and a bulge. It has very prominent spiral arms, and there's active star formation which is going on. While ellipticals are, they don't have these beautiful spiral arms. It has a smooth light profile, and it's dominated mostly by old stars, and there's little gas and dust. Right? And irregular galaxies they don't seem to have a specific shape. They don't look like elliptical, or they don't have a disk feature or so on. So they are asymmetric in shape, they are clumpy star-forming regions, and they are rich in gas and dust and so on. So mostly these irregular galaxies are disturbed galaxies, or these are galaxies in the process of immersion, where they have not been visualized after an encounter with other galaxies, and they show these kinds of random uh, forms and features. So astronomy from these galaxy images, the traditional machine learning first attracts the human design morphology. We specify what is the concentration index. We say what is the ellipticity, what is the Sersic index. We say Sersic index is 4, then it's elliptical galaxy, and the Sersic index specifies what kind of a bulge it has and what is the formation history of it, color, asymmetry. So these are the uh, human design morphological features which we train in machine learning. Then they train a model with these features, and then the machines learn to find and classify galaxies in these. In deep learning, we feed the galaxy images directly into the neural networks, and then networks may learn the spiral arm edges and bars. It identifies whether it's a smooth elliptical profile or not. It will identify tidal features and merger signatures, and it could see clumpy star-forming regions or not, and on its own recovers these features uh, uh, without us having to specify the features. So why this deep learning helps here is galaxy morphology contains complex structures, and raw images carry information that may be hard to summarize, right? So similarly, we can use this in classifying stars in the different spectral classes. The classes, as you know, are classified by the spectra, which are encoded in temperature and composition. Blue O stars are over 30,000 Kelvin, blue giants 10 to 30,000, and so on. And 3,000, less than 3,500 Kelvin, we have the red dwarf stars and so on, right? So the hotter stars are the ones which are on the left. O, P, R, A, they are hot stars, while G, K, M, these are the colder ones, which are the redder ones. So, in astronomy, what is a spectrum? A spectrum records intensity of flux as a function of wavelength, and the spectral lines carry information about the temperature, composition, gravity, activity, and motion. Right? So machine learning approaches measure spectral features like H alpha equivalent weight, calcium triplet strength, line depth, continuum slopes, and so on, and use them to predict the stellar type, temperature, metallicity, or various features. Deep learning approaches feed the whole spectra to the neural networks, and which learns subtle line combinations, captures broad continuum shapes, and can exploit weak patterns which are difficult to manually define. So similarly from light curves of variable stars or exoplanets, we feed these light curves, and from looking at the patterns, the periodicity and light curves, the machine learning learns the period, its amplitude, its skewness, the transit times, and various features. While in deep learning, by exposing it to a variety of exoplanet transit curves, as a planet is eclipsing a star, so you will have the intensity falls, and then it increases and it falls and so on. So these light curves are fed into these neural networks, and from these neural networks, it predicts what kind of a variables star it is, what is the exoplanet candidate, and classifies them. Okay, so machine learning approaches to extract light curve features, period, amplitude, rise in time and declination time, skewness, and the Fourier coefficients, and then classify into C feeds, RR, Lee-Ray, eclipsing binaries, or exoplanet candidates. While in deep learning, you feed the full light curve directly into a neural network, which learns dip shapes, learns periodicity and noise patterns, learns the transit like signatures, and it's useful for anomaly detection and to classify using the features it has learned. So the main differences are the aspect relationship we have in machine learning broad field, deep learning, the subfield of machine learning. The input data is often structured in machine learning, and in deep learning, often it is raw data. The feature designs in machine learning are human designed ones, while in deep learning, it's learned automatically. And the data requirement is in machine learning, it works with smaller data sets, and deep learning usually needs large data sets. Computation, machine learning can run on normal computers, while deep learning often needs very powerful GPUs. Uh, Interpretability often more interpretable, and deep learning is often hard to interpret. And the uses in astronomy of machine learning is catalog analysis, clustering, classification, and so on. And in deep learning, you have images, uh, we have spectra, we have simulated data and the light curves, and then it learns the features and it can be used in classification and clustering and so on. So the important distinction as we see our machine learning not is not old and deep learning always is not always the best choice, right? They are complementary to each other. So when machine learning may be enough for Gaia catalog data with parallaxes, proper motions, color magnitudes, methods such as these are given, you have very powerful algorithms like random forest, XGBoost, SDB scan, Gaussian mixture models, DB scan, optics, and so on, which may work well. And when is the deep learning better? When we are dealing with raw images from, say, Hubble, from GWST, SDSS, LSD, where you have images which come in, right? Like you must have realized that in Gaia, you have data which flows in, where you get specifically the features listed out in tables, while the data which we get from James Webb Telescope or Hubble or SDSS and LSST basically raw images, and deep learning can be useful because the spatial patterns are rich and very complex. Okay, so the final summary of what I've been saying is machine learning learns from data, usually using selected or engineered features. These are catalog-based problems, cluster findings, stellar classification, redshift predictions, population separations. And deep learning learns usually from multi-layered neural networks, often discovering the features by itself, like galaxy images, spectra, light curves, simulations, and anomaly detection. So remember, machine learning learns from features and deep learning learns from features. Okay, so this comes to, there is a question, I think. Let me see. Somebody has raised.
Hello, can I say something?
Yeah, please.
Okay, so I wanted to ask this question in the last class. Can machine learning and deep learning also be used to make analysis on Redshift or hot plasma analysis?
Yeah, of course. You can use both these techniques for these things, right? Yeah. So, Gayatri, how deep learning is different from unsupervised machine learning? Okay, so in machine learning, Gayatri, machine learning, finally we deal with features, where you have features which are specified, and from features which are human specified, like we specify what is the parallax, what is the color, and you have the features. For example, when we get data from Gaia, you are specifically, uh, we have realized, we know that when we are observing star clusters or stars, what are we interested in? Their uh, right ascension declination, their parallax, their color, their RG, RB, and so on. So when you have these features, so in unsupervised, we don't specifically specify that this is O star, B star, or so on, but all the same, the features are given there. Okay. While in deep learning, we don't have the feature space. This is which is much more raw, and the machine learns to find out the features on its own, right? So in deep learning, even when it's supervised or unsupervised, in unsupervised, the features are present there, and the machine tries to learn it through that, right? So in deep learning, we are dealing more with raw kind of data. In what format do we feed light curves in deep learning? You directly feed the spectra of it, right? In deep learning, you have the spectra which is directly fed, and it sees through a variety of these spectral images, and it can do that. Okay. Now we will go to the so now we will come to what these deep learning techniques are, and what we will try to understand what this convolutive neural networks are, and then we will run through some Jupyter notebooks and do that, right? So why do astronomers use machine learning? Like we have said, discussed many times, the modern telescopes, various surveys are producing enormous uh, image data sets, and it can be used for classifying millions of galaxies, finding faint gravitational lenses, or detecting supernova and variable stars, and in an automated way, and searching for exoplanet transit signals. So, what is CNN? A simple definition is a convolution neural network, or a CNN, is a neural network designed to learn patterns in the images. Instead of rendering an image as one long list of numbers, a CNN looks at nearby pixels together and tries to see. For example, even the spectra of stars, we can feed it the spectral graphs can be fed directly, and in deep learning it can do that. So a convolution neural network learns useful image features step by step. So if, for example, you have the astronomy image, then you have various convolution filters. We'll see examples of this. And we draw feature maps from it. And then you have the denser features, and then you do the prediction. right? So we will have a look at what we mean by these feature maps and how do we do that. So any image, a CCD image in astronomy is essentially a matrix. So I've given a simple matrix here. The image here has, say, 1024 by 1000, so many more. So this is basically uh, some kind of a matrix where numbers are given, and smaller numbers show lesser light, larger numbers show bigger ones. The image which is here and the matrix which here, they're not correlated, because you would have required a much larger image to show this image. This is an artificially generated image. So each number stores brightness, and brighter stars have larger values, empty sky has smaller values, and you have noise also, right? You have dotted points here. Okay, so for example here, I have an image of, this is an image, input image, and I run through a CNN convolution kernel, and I get back this image. And from here, you can see features. You can see that this is a ring. We'll actually run this in the Jupyter notebook and see how we get that. If you want, we can have a look right away. So I will just stop the share and share the other object here with my Jupyter notebook. Okay, see, for example, here's a demo of CNN for features extraction. So we import NumPy as NP, and from PI I'll import image, import matplotlib.pyplot from PLT, this is to be plotting. And I've downloaded this image, NGC 1566. It's a spiral galaxy, right? And I've the image path is, I put it locally. If you have it in some specific location, you have to write this here instead of this. Okay, so I run that, and then I'm loading the image open. I use image open, and I'm converting to the RGB. It was just a JPEG image, so I'm converting it to this and storing it to IMG. And I'm storing it as that image array as a NumPy error, right? So basically, if you see that this NumPy array, let me add here. So IMG, so just a minute, sorry. Yeah, so if we are plotting by imshow, you for a moment you might have seen that it was showing that it is an array there, and then this imshow is converting into this and showing what the image is. Okay. So for example, we have the this spiral image here. Yeah, similarly, I'm using here the GravLens JPEG, right? And I open the image, and it's showing the image. Okay. Then I convert this image into uh, grayscale. So RGB image I am converting into grayscale, and I am plotting it in grayscale, right? So you must be noticing that I am showing image CMAP as gray. You must be saying that it is looking, what if I don't have this written here? Yeah, and you will notice that it is not giving you actually grayscale, it is showing just because the IMSHO by default in uh, in Matplotlib uses the word is color map and it's showing it in this. So I specify that. But in case you don't want to say CMAP as gray, you can run this code. You can convert this totally into the grayscale image. And then when you'll see it in the grayscale. Okay. And when and run it, I will see it. Now I'm convolving this using convolve 2D image kernel, and then I'm applying the kernel which I have defined here. The kernel is an NPR of -1, 1, a 3x3 matrix, and I'm convolving it with this and getting the feature maps from it. And what we see is this input image which we have by 3x3 convolved matrix. It is giving you the feature maps, right? So you can see that it cuts down the color, it cuts down the various things, and it is just giving you the basic features. And then it becomes easier for machine to categorize different objects as different, right? So we will run the other one for the galaxies, and you see, okay. So I am getting the spiral galaxy image here, and I'm can see this. I'm using a Gaussian kernel using the Gaussian blur. So this will reduce the tiny star noise before the edges extraction. And then I'm using another kernel, Sobel kernel, for detecting the directional edges, right? Sobel X and Sobel Y. So this will find out the edges of it. Then I am using this Laplacian kernel, which will highlight the sharpened structures. And then in this, I'm applying all the three to the image, and then I will display it. So you notice that this was the original image, and by here we are just seeing the same thing in grayscale. But when I'm applying the Gaussian kernel, I'm smoothing out the thing, right? All the sharp edges are smoothened out. And then I'm using the Sobel edge features, which is pulling out the edges of these spiral arms. And then the Laplacian edge features will get only the features of it. And when we combine all the three ones, this is what we see. So it becomes easier so now the machines can look at different images after running through all these, and it matches and could say whether it's a spiral or not, right? We'll do the same filters which we have used here. Instead of the spiral galaxy, I will use this elliptical galaxy here, right? So I'll run it with this elliptical galaxy GFX image, and I'll run through the whole thing, and you will notice that this elliptical galaxies, when we are applying the Gaussian blur, anyway, it's a smooth, because elliptical galaxies are pretty featureless. They are they have a uniform smooth feature, right? So there's not much we have got here. But when we did get the Sobel edge features, we are seeing the edges here. Then we are applying the Laplace signal, and right. So when you run through images of galaxies, there are thousands and billions of those, you can very easily break up the image from one to the other and so on. Okay. So this is what it does. And yeah, so let's go back to the presentation. So we have seen examples where we have used actual images which are downloaded from net. We applied different convolution kernels, and we extracted various feature maps, right? And with these feature maps, it becomes easier for us to understand, right? So the edge layers, the early layers are, it identifies edges, it identifies corners, it identifies the bright spots, and it pulls out the small textures from the thing. And the later layers, it finds out the spiral arms, it can see the galaxy bulges, and lens. Yes. Yeah, I'm sorry. And you get the various features, right? So we could run these CNNs to classify galaxies as spirals, ellipticals, irregulars, or mergers. We'll see yet another Jupyter file where we see them in how we can identify these features well, right? So here you have a zoo of galaxies. You have barred spiral. This is what our Milky Way looks like. You have Andromeda galaxy. You have these filamentary cigar type of galaxies, whirlpool galaxies, and a variety of different ones. And these CNN models learn the shape directly from these pixels instead of relying only on the handmade features. Okay, so yeah, so another important thing is we get these confusion matrices when we run through these galaxy classification. And this confusion matrix is very important, which tells us how good your CNN is working. So for example, if we get this confusion matrix, it shows where the model is correct and where it's getting confused. So if you see here, the prediction is on the x-axis and the true ones are here. So along the diagonal, you have spirals which have been identified as spirals. You have ellipticals, which are identified as true ellipticals, and irregulars, right? So 86 of spirals, which were spirals, have been detected, right? 88 of ellipticals are predicted correctly. And similarly, irregulars, right? So this tells us that about, if you add them up, 86, 88, and 88, we are getting 262 out of 300 galaxies, and which is giving us approximately, if you divide 262 by 300, we get 87.3%. So 87.3% of time, this CNN has correctly predicted, right? These other numbers which we see here, it shows that 4 spirals, which were elliptic, irregulars, were predicted as spirals, right? Only 4 of them. And 7 ellipticals were identified as spirals. And here we'll see that 5 irregulars were identified as wrongly identified as ellipticals and so on. So basically it shows that off diagonal, we have been, which are not lying in the diagonal. These are the elements which have been wrongly predicted, and which is a small number, less than 13%, which are wrongly predicted. So this neural network is running quite fine. And we can also see from this confusion matrix that the major problem the CNN has been having is between ellipticals and spirals. You can see that if you count which were ellipticals, which have been identified as spirals, there are 9 here. And right, and spirals, which were 7 of the spirals, they were ellipticals but were found as spirals. So you can see that the largest confusion it has had is between spirals and ellipticals, right? But overall, right? So this confusion matrix is important to understand and make sense of what is happening. So this image, which we have already played around with, it's a gravitation lens, can look like an arc or a ring around a massive galaxy. And the neural network, your deep learning algorithm, will be able to pull out and say whether it's an elliptical galaxy or whether it is a gravitational lens or what is it. So this is useful because lenses are rare in large surveys. So it can scan through a lot of large surveys and identify these features and pull out those images which have this kind of a feature. Right. So similarly, the exoplanet transits. When a planet crosses in front of a star, the star becomes slightly dimmer, and the CNN or neural network task is we put the light curves or image representations, and the output is whether it's a planet candidate or not, right? So by looking at the light curve, the CNN would tell whether it's a, and then specifically can look into these in detail, right? So training a CNN, CNN learns from examples. You have labeled images. We don't specify features, but these are labeled images, right? In fact, this is what, then you have the CNN, it predicts, and then it compares with the true label, and it feeds back in post. So the model changes its filters again and again until it predicts and improves. So here's a tiny CNN, a small Keras style of example, which we'll be using, where we have used in fact convolution 2D, and you have max pooling 1, you have flattening, you are looking at the dense regions, and we have, you are softening these. So this could classify images in 3 categories as spirals, ellipticals, or regular, right? This is a Keras style example, which can classify them as spirals, ellipticals, or lenticulars. So some important things we have to take care of where beginners can make mistakes. Training on too few images, right? That's one thing. You have to have sufficient number of images to train the neural networks. Then testing on images that are too similar to the training set. You may test it on images which are very similar to the training set. So this will not show how robust it is, right? So it's always better to test it on, right? For example, if you have trained for elliptical galaxies for many which are face-on, and you are testing also on the face-on images rather than on elliptical galaxies, spirals which are slightly tilted, and you are trying to see how good your CNN is, not right. Right. So if your training set and your testing sets are too similar, you should try to avoid that. Ignore class imbalances, for example, many normal galaxies, but very few lenses. Forgetting that CNN can learn telescope artifacts instead of astronomy, right? We should realize that CNN can get slightly fooled by the artifacts which can get created, right? So you have to take heed of that. And reporting accuracy only without checking the false positive and false negative, right? So you have to keep an eye on the false positives and false negatives. And just saying that how successful, like in the confusion matrix we saw, just specifying that 87.3 times it has been successful is not sufficient. But it's also important to realize that it is making major errors or mistakes when it's trying to uh, distinguish between spirals and ellipticals. There's not much of confusion between irregulars and ellipticals, irregulars and spirals, but there is a bit of confusion, right? So one has to. So good practices in astronomy and using CNNs is to split data into training sets, validation sets, and the test sets, right? Use realistic noise and telescopic conditions, interpret misclassified examples, compare with simpler baseline methods, and use explainability tools to see what image regions influence the predictions. So the key message is CNN is powerful, but astronomers must still check whether the models learn real astrophysics from it or not, right? So you should be careful that it is not picking up artifacts. And so a take-home image, the CNNs are designed for image pattern recognition. Convolution filters learn local visual features. Deeper layers combine simple features into complex astronomy structures. CNNs are useful for galaxies, lenses, transients, exoplanet searches. And good validation is essential, right? So with this, we come to an end of this, and we will go back to our Jupyter notebook. Yeah, so there is a good paper which we'll share with you. It's called Convolution Neural Networks of Galaxy Morphology Classification. And yeah, I have made this Jupyter notebook on using that as a guide. That paper which has it tells you how CNNs can be used for galaxy morphology classification. And I've built this notebook on that. And I've built it in two ways, using TensorFlows and also trying to avoid TensorFlows, because on certain simpler machines, we would have problems running with TensorFlows. So this particular one, which I'm showing now, is without using TensorFlows. I'll share with you another way you use the TensorFlows in that. Okay. So here we are using NumPy and Matplotlib. So the models which we are using here is specifically on generated data. These are intentionally small for educational purposes. It trains a real simple CNN layer from scratch using NumPy. So you can see the core idea without fighting with deep learning installation issues. That's why I've kept it simple here. So if the first block is where we are importing all the required libraries, import math import NumPy, then we matplotlib, pyplot, SPLT, and NumPy library for slide these things. Okay. Then we have this from NumPy random seed we are giving 42. And like specified earlier, this is for if you run the file repeatedly, you will get back the same results. You continue to keep the same random seed. Okay. And these two commands are optional. This is basically to see what kind of NumPy version you are running and what matplotlib is running, right? So NumPy version is 1.26.2 and yeah. Okay. So yeah, so we are just important. So the case studies, the code is built around this article, as I mentioned, convolution neural networks with galaxy morphology. Yeah, using this Kaggle galaxy morphology task as a CNN case study. And the important ideas which we use are the inputs are these galaxy images which we are generating. It targets what population of morphology labels with values 0 and 1. The task types are regression over probabilities, not ordinary single class classification. Pre-processing. We crop and downsample the images to reduce memory and focus on the central galaxy, right? When you download images from, say, Hubble survey or so, we may have larger ones, but then you crop it, you just pull out, and cropping can be done either in Python or you can use IRAP or different tools to cut out these stamps from that, so which we are, right? And augmentation, we rotate and flip the images because the morphology is largely orient preserved, orient invariant. And the model, the idea is the CNN layer extraction, visual pattern, sigmoid output productions of probability-like values, and the loss and metric mean squared errors here, and the root RMSE. So in the article which we have, it reports that these galaxies whose setup uses 37 different output attributes. To keep this notebook beginner friendly, we are using only a four simplified model outputs, right? Instead of using 37, which is there, here we are only using 4 morphology features too, which is the smoothness factor, the disk, the edge on, and the spiral, right? Okay, so now let's run through this. So we'll first create a tiny synthetic galaxy data sets. The real galaxy zoo images are large and must be downloaded separately. I have towards the end of it the code which shows you how you can download the larger data sets. So here we'll be creating these synthetic data sets. And to make this, this is basically done to make this notebook run anywhere and create small synthetic galaxy-like images. And the 4 synthetic images includes smoothness, the edge on, this spiral, and the oddness, the regular galaxy clumpiness, and so on. Okay, so this is the one which is creating these data sets, right? So this code is coordinate grid size. Yeah, the size is being defined, which we are running it here. And it returns XY coordinate grids in the range -1 to 1. And this NP linspace, we have used this from -1 to 1. And the size is specified as we run it. And the data type is the NP float 32 floating point. So we have XS, XY. We create this mesh grid. Okay. Then the rotate coordinates is by rotating it. It's basically because the features are invariant under rotations and so on. It doesn't matter whether you see an elliptical course galaxy by 30 degrees or 90 degrees and so on, right? So to do that. And this is to add stars, yeah, in that. And we are making synthetic galaxies using this. Okay. And yeah, so this basically is constructing this and the images. Yeah, so here's the block which explains this. The above cell creates the teaching data set. The helper function builds the coordinate grid, rotation coordinates, adds small star-like pixels, and then generates 4 simpler galaxy types. Each synthetic image is paired with 4 probability-like morphology targets: smooth, disk, edge-on, and spirals. And these targets imitate the article's key idea. In that, like I mentioned, there are 37 different features, but here we are only playing with 4. That Galaxy Zoo labels these both proportions rather than a single hard class label. And at the end makes this data set and collects many examples into X for images and Y for the targets, right? So here it is. So it has created the spiral, into the smooth spiral and the odd features. Okay. And what that block has tested, this is it's a visualization function. It displays a small sample of the general galaxies. For each image, it prints the synthetic galaxy type and the 4 target values above the prompt. And this is useful before the training because it lets you check the data and label, and labels look reasonable. Then we are training, right, for validation of that. We are the article says that if you train it on 80% of the set and retain 20 of them for validation, that's a better thing than to train it on 90 and check it on with 10% of those things. So that's what we have done. So we'll restrict to what is suggested here. And we are training on the 80% and keeping 20% as for the testing. So a galaxy, the data augmentation with rotation and flips, the galaxy remains the same kind of galaxy even after rotating by 90 degrees or by left or flip or the up and down flip. This is why we use these random orientations and flip these augmentations, and the function below is applied to these transformations. And this is what we get, the augmented training examples. So this function performs data augmentation for every image in the batch. It randomly rotates a galaxy by 0, 90, 180 to 70 degrees and may flip it by left to right or up and down. And this is appropriate for galaxy morphology because the galaxy type should not change because the image is rotated or mirrored. The final, this AS contiguous array, it calls to prevent array layout issues and can happen after the NumPy flip rotations are done. And we build a tiny CNN from scratch with NumPy. And this model is deliberately small. The images, trainable images are 5 by 5 cross 5 convolution filters. And this is RU activation, 2 by 2 average spooling, flattening, then dense sigmoidal output layer and smooth disk edge and spiral, right? Okay, and this is what it does. And this cell defines a tiny CNN sigmoid, keeps each output between 0 and 1, which matches probability like morphology labels. The root mean square error measures the prediction errors. The convolved 2D same forward applies learnable filters across each image. And average pool 2 cross 2 reduces the feature map size. And the initial parameter creates the trainable weightage. Weights, and the forward function combines these steps. Convolution, REU activation, pooling, flattening, and so on. And a short test at the end of the check to test these models can produce 4 predictions image before training it. So you train it and you running it, yeah, and you are getting the root mean square error, which is 0.43, 0.04, 0.43, and so on. So this, yeah, so epoch 1, 5, 10, and so on. And if you, this will tell you that train mean square error and what is the validation mean square error, right? So it tells you this function plots the train history, and the first graph shows that mean squared error, and the second graph shows the root mean square error. The training curves tell us how well the model fits the training, while the validation curves tell us whether the learned pattern generalized to unseen examples. And to evaluate the predictions, we run this and we see that validation is 0.23. And in each one, the smoothness for each one disk edge on, it shows you the root mean square in the errors in each of these. So it basically says how well it has picked up the features of the smoothness or the edges and so on. And here we see finally how it is picking up the features and identifying these things. Okay. So the various filters it runs through, and this is how it maps the real galaxy zoo task. For the real galaxy zoo, you would have to replace the synthetic data sets with the actual image files, and you have to change the 4 output labels with the 37 ones which have been suggested in that. Right? So you have to load the image by galaxy ID, center crop the galaxy, resize the downsample ones, normalize the pixel values, predict these things, and run it, right? So this is the block which will help you do that. But I will not run this because we will have to download these data sets. Yeah, so you'll have to uncomment it and run this. But before that, you'll have to download and keep those the data in the specified path and directory. Okay. So so with this, I can also show you if you want to run this with the TensorFlows, then we'll open the Google Colab, and that's where it is running well. Just a minute. I will share. So let me go to Lab, and I'll share this notebook too. Uh, yeah, so okay, so here we have, right, here we'll be using TensorFlows and so on, and again with the same one, but it's here we'll be importing TensorFlow as TF and import this, right? Yeah, so this is the previous one which I ran, it was running without using the TensorFlow, but this is the same one where we use TensorFlows, and I will share this with you, which you can run it for visitor. So it's running well, and basically it's doing the same thing using the TensorFlows and so on. Okay. So with this, I will stop now. School patient. Yeah. So, so if there are any questions, we can discuss. In the meantime, I will share these things with you and in the chat window. So you can run this thing in your Google Colab, and yeah. So again, this has this block where you can download the actual, from Zoo image and use all the 37 different parameters which is done and run it in a more detailed way. Okay, so just a minute. I will open the chat and upload the I'll upload the images also. And also the PowerPoint presentations. So, I think with these you should be able to run this and then see how it's going. And if there are no questions, there's a just any question. Yeah, so these values, there's somebody who's asked, what do we do with the values of the matrix for the kernel representations, right? So you have to use different matrices for getting different things. There are certain specific ones which I have specified there, which you can use. So depending on the image and depending on the size of the image and so on, your kernels have to be different, and different kernels will pull out the different features in it, right? So you must have seen that we have the Gaussian to pull out create the Gaussian blur and to pull out the features and sharp ones. You have different values. And the best thing for you to do is you change these kernel parameters, take an image. So start off with take a simple, say, smooth elliptical image of an elliptical galaxy. And you have a kernel which I have given for that one. And you change the kernel values. So it's a 5 by 5 kernel for the specific image which I have given you. And then you give the different values of it and see how it works, right? So you will have to practice time and again, play around with it to understand how to get different features. How do you get the features of edges, get the features of irregular things and all in the kernel matrix to do that, right? So that the whole thing is an art. Don't use these as a black box, but it's best that you understand what you are doing and run it. So the synthetic images which I have shown are very simplified images, and it's best for you to run different kernel parameters on these images and see. And then you can specifically take one spiral, one irregular, and one elliptical galaxy and run with different kernel parameters and see how it is pulling out the features. And in the code, as you must have seen, I've shown you that you can how to see the image after running the kernel, and you get the features, how to save it into a file and visualize that, right? So yeah, so you can do that and do it. Okay. So any more questions? So I hope you have understood. So basic idea to recap what you are doing is you have machine learning techniques and you have deep learning techniques. And both are being used in astronomy research, right? And both are complementary ones. Okay. So the question is, which one should you use? It depends on the problem you are studying. Okay. And what we have seen is, if you have features, the data which you are using, you have features which are listed in that. For example, you are using catalog data from TUMAS or from Gaia data and so on. Then you use the machine learning techniques are much more useful and much more, because the features space are specified there. And from those features, you can train your machines to pick up the features and to do the classification or um, uh, clustering and so on. But when you are dealing with, say, image data, say, for example, you are getting the raw data as images, say, from James Webb or HST, these are images, then the deep learning techniques are much more useful there. Okay. Deep learning techniques are used when the data is much more complex, much more varied, and you want the machines to pick up the features on its own, right? So deep learning is a much more powerful technique, and it is indeed it can raw data in much more efficient way. And so deep learning is used when you are using large amounts, tremendous large amount of data, then deep learning techniques are much more effective and useful. And when the data is much more complex, where we do not specify specifically these features, to which on the basis of which you are classifying or categorizing them, but you are doing it at a more uh, complex. The machines are more effective and smarter in doing that. Okay, so we have done 1.5 hours of session, and
Hello, sir.
hello, yes.
Yes, sir. I want to ask a question. Why you were explaining the CNN method? I From your notebook I saw that you were also saying we could train some set of data using. So I want to know, because while you were explaining through your slide, you said machine learning uh, can be done using, like, by training data sets, while for deep learning, yeah, it is the contrary. So I don't know how we are able to train data sets, because from your notebook I saw that you were also saying that we can also train data sets while doing the CNN method.
Yeah, so suppose you have these surveys and you have large amounts of data, and from that you want to specifically pull out on the basis of certain features you are interested in. Then you build your own CNN models, right? Where you are giving importance to specifically a certain number of things, right? Either you have these CNNs which are there available, like you said, in public domain, and you use that to do it. But specifically, if you are interested specifically, you are going to give importance on certain features which you specifically want to look at, and you want to pull out those objects or classify or categorize them on basis of specifically some features. For example, I have a lot of spiral galaxies. You have thousands of images of spiral galaxies, but I'm interested in those spiral galaxies which also show a ring feature in it. Or I only want to pick up those which has a bar and a ring, right? So spiral galaxies itself have many more specific features which are uh, which are important and so on. So you can build your own CNNs, and where you specifically train, you specify what are the features you are looking for, and you train your CNNs to pick up these features. And then from these CNNs, you run it on the bigger data sets to specifically pull out those features which you want. Or suppose you are looking at exoplanet or light curves of stars, and you are specifically want to pull out from all the light curves RR Lyrae ones, right? So you can build your own specialized CNN models, which will pick up specifically those RR Lyrae ones, where you specify exactly what kind of the features you are giving importance to, right? So that's why I was showing you how you can build your own CNN and train them and use them to uh, uh, categorize. I hope I've answered. Yeah, is
Yes,
it?
sir. Yes,
Yeah,
sir.
yeah.
Thank you, sir. Also,
Right.
I don't know if I can ask one more question. Can I ask the question? One more question, please.
Yeah, sure, sure.
Yeah, thank you very much, sir, for the wonderful section and how you've taken us so far. I all through the course we've learned that why if we want to do analysis, we can use the DS9, we can use the charter, we can also use machine learning, deep learning for making analysis. So I want to know. I believe in all of this method of making analysis, there each of them could have some flaws or some error bars whereby while making using any of them to make your analysis you could obtain some errors. So I don't know if can you specify which of them is more viable in
Yeah,
getting a good result.
yeah, yeah. Yeah, so you are right. So when you are dealing with, say, images, you can you can use DS9 as well, right? You can use DS9, and DS9 also very in a simplistic way allows you to not only access the data from the net, right? You can query the data, you can download the image, you can do some contour plotting of it and see some features in it. You can see how the contours look and you see whether it is a disturbed spiral or not, or what is the Sersic index and other things and all. But you can do the same thing using Python. You can use the same thing using Galfit or IRAF and so on. So there are many ways where you can do that. But the sophistication at which you are doing, it varies from one tool from the other, right? So many of these virtual observatory tools, like you have the DS9 and you have TopCat and other things that are used specifically for the different things. And the same thing can be done using Python. Okay. The interesting thing or important thing of doing it in Python is if you write the code, see when you are using, say, DS9, you specifically do one by one for each image and you analyze them one by one. But if you can do it using Python, a programming language, then you can automate it. And in one go, once your code is running well, once you try it on one image, one sample, and you see that the whole thing is running perfectly well, then each feature you are in the same code, you are doing the contour plot in the same Jupyter notebook, you are looking at uh, it calculates the Sersic index and tells you what kind of bulge and core it is, and it does the whole set of deal. You can you can run the code into hundreds of images in one go, and you will get the results in an automated way. And yeah, so it simplifies your work tremendously if you do it through Jupyter Notebook, or you use these machine learning techniques and so on, right? So this is the thing. You can automate the whole thing, and instead of running it, and in fact, what you can do in DS9 is very, very basic. You can, when you do the same thing, when you want to, even in DS9, you get to understand what is the Sersic index and so on. But when you do galfitting and you doing galfit or galpy, you can do it in a more sophisticated environments. Okay. So advantage of doing it through the techniques which we are showing you now gives you the power and strength of it takes give you initially you spend a lot of effort in building the code, But once it is done, then it becomes very easy for you to run it on a data set which has, say, hundreds or thousands of things, and in an automated way gets it, and in an automated way uh, uh, categorizes your results, and it also can, in an automated way, help you analyze, compare the results of one another, right? So, yeah, so I think have I answered your question?
Yeah, thank you, sir. Thank you, sir. Thank you very much.
Yeah, so if we have some more time, maybe I will do a little more. Let us use the time, and let me. Peng was also supposed to be handling 1 hour. He was supposed to do, and 1 hour I was to do, but unfortunately he had some problem with his laptop. I think what he wrote to us was it fell in water. So in the morning he told us that he has some problem um, uh, with his laptop, so he is unable to handle it. So I will see if we can do something more while we are at it. Okay, uh, maybe we'll try to run this uh, principal component analysis, PCA, which we had touched upon in the previous meeting. Just a minute. Just a minute. I'll share. Just a minute. Just he's taking a risk and hoping that this notebook runs right away. It's running in my Linux side, but I have not tried it in Windows. So let me see whether if there are some errors, we'll try to handle it. And yeah, so we have this principal component analysis. And like we discussed in the previous last session, this principal component analysis is used. It's a very powerful technique to reduce dimensionality. When you have data and you have a lot of parameters in it, and if you want to find out what are the main ones, the ones which are the most important, which are playing a role in defining something. For example, suppose I have a factory which is in a city which is going to produce cars, and we have to calculate what kind of the price of that vehicle should be. Okay, and the data which we have for the city, the location of the data, the availability of resources. See, we require land, first thing to set up a factory, we require large land. We require water for that. We require iron or whatever elements which we require. Then we require the labor the labor cost, and we require the cost of electricity and so on. So you have multi-parameter data, and we are seeing that the price of the car which we are defining would depend on all these things. So you have the location, that you have cost of transport of resources, labor charges, you have the cost of electricity, etc., etc., etc. And we want to find out what are the most important things which is going to play a role in defining the cost. Everything does play a role, but which are the principal components, right? We are doing it for PCA 2 or 3, or how many important components we are doing. So the principal component looks at the variability in each and sees how the data is scattered. So it finds out the direction where the variability is the least and where it is maximum. And it uses these to find out which are the most important parameters, which is the variability in one which is making the maximum different on the cost, and which is the other one which is the least important thing, which is playing. Okay. So similarly, when we are looking at, say, the galaxies, and we are trying to say what is it which is going to tell us which is, whether it's an elliptical galaxy, whether it's a spiral galaxy, whether it is this. So we have various parameters which is defining it. One is how is the light falling, the smoothness of the light profile of it, right? Whether it's the Sersic index, which is important, whether it is the clumpiness in the object, which is important, right? So the principal component analysis looks into the highly featured space and pulls out the most important one. So it can be used for in high dimensional data sets where you have spectra, images, and catalogs, and in removal of noise or instrumental effects, and so on. Okay. So the first set is you set up the by importing NumPy, the NP, Matplotlib, and all those things, and sklearn decomposition, PCA, and pre-processing standard scalar, which we have seen here, which normalizes data. So when you have various parameters and the values, they have to be normalized, which we saw in the last term. Suppose one column has data in 0.01, 0.2, 0.5, 0.3, and the other one is in 20, 30, 40, 50. So if you don't normalize it, then your analysis, regression, and various things, PCA, may start giving more importance to these larger numbers. So you have to rescale it. You have to realize that in one parameter, these 0.1, 0.2, what do they mean? The basic nature of data is it has to be small, right? So the scalar re-normalizes it so that the mean comes somewhere around 0 and standard deviation is 1. So it re-normalizes, and then it does that. Then from AstroPy, we have data which is used to import these data files, and astropy.io is import fits. I think this fits file has been handled and done by Alexei, right? So you are familiar with what fits files are and so on. So we are downloading from this URL. I hope this works now with this internet connection. So I'm downloading from DSS this data of spectral reduced spectral 1. We have downloaded that, and we'll do the pre-processing first of this, and we are looking at this galaxy spectra. Okay, so look at this. The scalar in this variable this is basically we are going to the whole flux this is scaled flux, right? Flux reshape -1 to 1 and flatten it. And then we are plotting it, specifying what is the figure size and so on. And we have the label, this is the original one, while the scaled one, right? You notice this blue one is the original one, and it is going up to 800,000. But when we are rescaling it, you see it is here. It is the mean is lying somewhere around 0, and the height is coming to 1, right? So this is what this scalar is doing. It is just, then we are applying, doing the spectral, we are doing the PCA, principal component, and we are using this PCA with n components as 2, right? So we are basically, if you want 3 components, then you should change it to component 3 and so on. Okay. And it is fitting the scaled spectra with the scaled spectra data. We are fitting it with this PCA.fit transform and storing it into the results. Okay. And we are printing out the variance of it to understand how good these fits are. The variance will show you. Yeah, the variance. Okay. So when we are looking at this one, and we are looking at the in the eigen spectra, you see that the projection of data in the PCA space, we have the principal component 1 here and the principal component 2 there, and it is plotting it into this, and the spectral indices are given in these colors. So those which are yellow shows the spectral index to be around 9, while ones which are these dark colors are around 0 and so on. The spectral index is here. And the interpretation of this, we see that here is the spectrum reconstructed using PCA. The original one is given in blue, and the one in the 2 PCA space is given here. And we see the conclusion is the PCA it's available to customers who are working with high dimensional data, and it shows how to standardize it, how to compute the principal components, how to visualize the set, and right, how to apply this PCA to your own data sets. Okay, so you can run it on your own data sets here. So this was the data which we had downloaded from it, and we see that the 2 PCAs which have the variance goes from 0.12 to 0.11. So the largest variance which we have is 0.12, and the smaller component is here. Right, so right, so this is, it is spreading it into this, and it will show how the whole spectra which we have is being done. Yeah, so it basically reduces your data into components. Okay. Okay, so maybe we should stop with this, and if there's specifically any issues and all, we can discuss them, or else we will stop for today.
All right. Thank you very much, Najam, for the presentation. So participants, please, for those who did not check, if you go through the chat now, you will see the resources shared by Professor Najam. Please kindly download them if you haven't. I think they are very essential. A good number of them are images as well as notebooks and PDFs. So please, for those asking for resources already shared, please kindly download it. We'll give you roughly 5 minutes to do so before we end the meeting. Yeah, but in the meantime, yeah,
There's
Prof.
something somebody wants to ask, we can discuss it, or else
Yes. Okay.
I'll
Yeah, if you have any question, please indicate or put in the chat so the Prof will answer them.
And for PC also, if required, I'll share another. I've shared the one which I've discussed now, but with a more concrete example, I can show you how PC is really effective. Rather than using the spectral data, we can use other one, a more simplified one where we can see which are the main features with them. Right. So I'll share it with Libo and he'll share it with all of you. Yeah. Okay. Okay, so Libo, so I think there are no questions, so we'll stop with this. Okay.
Hello, Prof.
Okay then. See you then. Bye bye.